Hello everyone. In this session we will discuss one simple continuous beam, how to analyze this beam by using Kani's method. So the given problem is something like this. Okay. In this continuous beam we have three spans, span AB, BC and CD. On the span AB, which is of 5 meter, it carries a UDL of 10 kilonewtons per meter, and on the span BC we have a concentrated load at a distance 3 meter from point B and at 1 meter from point C. And on the span CD we have a central concentrated load of magnitude 40 kilonewton. The span CD is about 5 meter. Here you can see the variation of the I value is there. So for the span AB, the I value, that is moment of inertia, is I, and for span BC the moment of inertia value is 2I, and for CD span the moment of inertia value is I. We have to analyze this beam by using Kani's method, and we need to draw the bending moment diagram. See, here in the problem they have asked only to draw the bending moment diagram. So whenever they have asked to draw only bending moment diagram, there will be slight changes at the end. That is, we don't need to calculate the support reactions. We can directly draw the bending moment diagram with the help of the second approach what we have discussed in the previous classes. Okay. So as like the slope deflection method and the moment distribution method, the first step in the analysis of beam in the Kani's method also remains same, that is the estimation of the fixed end moments. So let me start with that solution. So the step number 1, it is the fixed end moments. From the last two modules we will be discussing how to calculate the fixed end moments. So here also we will have the same kind of formulas to work out the fixed end moments. Okay. So for the first span you can see we have a UDL on the beam or a UDL on the span. So the fixed end moments for span AB, that is MFAB, is equals to, it is minus WL square by 12. Okay. So here the W, the magnitude of the load, it is given 10 kilonewton. So it is 10 into L. L is nothing but the span of the beam. The span is 5 meter. So it is 5 square divided by 12. So which yields to minus 28. Minus 20.83 kilonewton meter. So this is the fixed end moment for the span AB, that is at point A, that is MFAB. Now similarly I have to calculate one more fixed end moment at point B, that is MFBA. It is plus WL square by 12. Here only change in the sign, everything will remain same. So even you can expect the same answer, only it is change in the direction, that is plus 20.83 kilonewton meter is the fixed end moment at point B, that is MFBA. Now similarly for the second span, for the span BC, we need to work out the fixed end moments, that is MFBC is equals to, so you can see here on the span BC we have the eccentric concentrated load. So as the load is eccentric, so we need to use the formula WAB square by L square. So this is the formula to work out the fixed end moments whenever we have the eccentric concentrated load. So minus, so here the W is 25 kilonewton, so it is 25 into A. The span A is the distance between the point to B to the load, that is the distance A, it is about 3, and the other distance it is 1 meter, so it is 1 square divided by total span is 4, so it is 4 square. So this yields to minus 4.69 kilonewton meter. So this is a fixed end moment for the span BC, that is MFBC. Similarly, we need to work out one more fixed end moment for the same span, that is MFCB. MFCB is equals to, it is plus WA square B by L square. So here plus the load is 25 into A. A will remain same, that is 3. So it will be 3 square into B is 1 whole divided by 4 square. So which yields to a value of 14.06. So it is 14.06 kilonewton meter is a fixed end moment. So these are the two fixed end moments for the span BC. Now similarly, we need to work out for the span CD, that is MFCD. So you can see here on the span CD we have a 40 kilonewton concentrated load acting exactly at the center. So you can use the formula minus WL by 8. So W is the magnitude of the load, that is it is minus 40 kilonewton. The total span is 5 meter divided by 8, which gives you a value of minus 25 kilonewton. Minus 25 kilonewton meter is the fixed end moment at C. The last fixed end moments, that is MFDC, is equals to, it is plus WL by 8. So the formula is same, so you can expect the same results divided by 8, so which gives you plus 25 kilonewton meter. Right. So these are the 6 fixed end moments for the span AB, BC and CD. Now we need to go for the second step. Okay. So as I told you in the earlier also, the second step, that is estimation of the relative stiffness and the rotation factors, which is very similar to the distribution factor what you have calculated in the moment distribution method. Okay. So I will erase this. Step number 2. Relative stiffness, that is the value of K, and the rotation factors, which is we have designated it as U. Right. So to calculate the rotation factors, we need to go for a table. The table is very similar to the moment distribution factor table what we have done in the moment distribution method. So here first we need to note down the joint. Okay. Then the members at the joint. Then we have to calculate the relative stiffness, that is we need to work out the value of K. After the K, total stiffness, that is summation of K. Then we need to go for the distribution factor, which you already know. Then the last one is rotation factor. rotation factor u is equals to, it is minus half of k by summation of k, or even you can write it as u is equals to minus half of distribution factor. Anything is fine. So k by summation of k is nothing but a distribution factor. So you can use any the formulas. Okay. Now, if I see the given loading diagram, you can see here there are two intermediate joints, one is B and another one is C. So I will note down them, one is B and another one is C. Right. Now at point B we have two members, one is BA, another one is BC. Okay, so I will note down those here in the members, BA and BC. These are the two members. Okay, and similarly if I come to the C joint, you can see at the C joint we have two members, one is CB and another one is CD. So here we have CB and CD as the members. Okay. The relative stiffness, the value of K we need to determine. So to determine the relative stiffness, we usually observe how is the far end condition. See, for example, if I want to determine the relative stiffness for the BA member. So for BA member, B is the near end and A is the far end. So how is the far end? So we need to work out the far end. So far end here for BA member, B is near end and A is far end. So here far end is fixed. So for fixed far end, the relative stiffness, it is I by L. The relative stiffness formula is I by L. So how much is I value? So I value is I, no change. So it is I by L. L is 5 meter here. So this gives me a value of 0.2I. 0.2I is the relative stiffness of member BA. Now for member BC, B is near end and C is far end. So how is the far end? So far end here it is a continuous or it is an intermediate support. So in the structural analysis we treat all the intermediate supports are fixed. So that is a basic assumptions what we have done in the structural analysis. All the intermediate supports are treated as the fixed support. So C, it is an intermediate support. So this support, even though actually it is a simple in nature, it is treated as fixed. Okay. So now for BC member, C is far end and the far end, as it is an intermediate support, we treat it as a fixed support. So for fixed support, the relative stiffness, it is again I by L. So I value here for BC member, it is 2I. So it is 2I by L is 4 meter. L is 4 meter. So that gives you the value of K as 0.5 I. Right. Similarly, if I come to the joint C, for joint C we have CB and CD as the members. For CB, C is near end and B is far end. So here the far end is again as like previous, it is an intermediate support and all the intermediate supports are treated as fixed. So it is I by L. So I value is again 2I, L is 4 meter, so this is also 0.5 I. Lastly for CD member, C is near end and D is far end. So here for the given problem, the support D, it is fixed in the nature. So the relative stiffness, it is again I by L. I value is I, no change. So it is I divided by L. L is 5 meter. L is 5 meter. So this is 0.2 I. 0.2 I. Now the next one is total stiffness at each joint. So we have to work out how much is the total stiffness. We have two joints B and C. For B joint, the total stiffness, that is 0.2 I plus 0.5 I. So it will be 0.7 I. Right. Now similarly for C joint, we have two members, 0.5 I plus 0.2 I. So this is also 0.7 I. Right. So now this calculation of distribution column, it is an additional. You can calculate this or you can directly calculate the rotation factor as per your convenience. If you calculate the distribution factor, minus half of the distribution factor is nothing but the rotation factor, or else you can use this formula directly to calculate the rotation factor. It is up to your convenience. Okay. So here if I calculate the distribution factor, so distribution factor, it is nothing but it is K by summation of K. K by summation of K is nothing but relative stiffness divided by total stiffness, that is 0.2 I divided by 0.7 I will get cancels. 0.2 by 0.7, it gives you a value of 0.28, right, and 0.5 by 0.7, that is 0.5 by 0.7 gives you a value of 0.72. 0.72. Remember, the total distribution factor at any joint, it is exactly equals to 1. If you add these two, it should be 1. This is a cross check what you need to do in the step number 2. So here itself you have, if it is not 1, then assume that your calculation has gone wrong. So if this is wrong, all the further calculations will be wrong. So please verify this. Similarly here, 0.5 by 0.7, so this is gives you 0.72 and 0.28. 0.2 by 0.7 gives you 0.8. So now the relative stiffness, rotation factor. So rotation factor is equals to, either you can use this formula or this formula. I will use this. So U is equals to minus half of the distribution factor, minus half of this. So how much is the minus half of this? So it is minus 0.14. Exactly half of this, just use the negative sign. So half of the 0.72, half of 0.72 is minus 0.36, minus 0.36. So minus 0.36 minus 0.14. So now here we have one more cross check. As like the total distribution factor at any joint must be 1, the total relative stiffness at any joint must be minus 0.5. So if you add these two, it will give exactly minus 0.5. Similarly, minus 0.5. Right? So if these values are correct, then you can say the step number 2 is correct. Right? So now we need to go for the step number 3, which we call as Kani's table. Okay. So this is step number 3. The Kani's iteration. It is a kind of iterative step, as like a moment distribution table, where we need to calculate the many values again and again. So here in this step, we used to calculate the rotation contributions. So I think you remember the rotation contributions we have discussed in the last class. Okay. So step number 3, step 3, it is Kani's table. or even you can write it as Kani's rotation table, Kani's rotation contribution table. So, I would like to keep it simple, Kani's table. So, here in the Kani's table, the representation of the table, it is little bit different. It is not just a table, it is something different. Let us see how the Kani has represented the table. So, what Kani has done, he has shown the given structure or the given frame as it is, just by replacing all the intermediate joints by boxes, and they have not shown any given loadings. Okay. See here. So, I will show the support A as it is. See here. I will show the support A as it is. Then I will show the span AB as it is. No change. Okay. So, now instead of an intermediate joint, I will show represent it by a box. I will represent the joint by a box, right. Next, I will represent the span BC as it is, the span BC. Now, I will show the joint C by another box. Okay. Then I will show the span CD as it is, then the support D. So, here what we have done, we have just replaced the the joints by boxes. So, I will go for a little more further modification. So, in these big boxes, I will show one more small boxes, okay, and I will join these lines. So, this is how the Kani has represented the joints. Similarly, here also, okay. So, I will join these, right. So, this is end A as we know, this is joint B, this is joint C, this is joint D. So, this is how the Kani has represented the table, okay. So, it is not just like the other tables, it is something different. Now, what are the things we need to note here? So, first of all, we have calculated the fixed end moments. So, we have to represent all the fixed end moments in the Kani's table. So, here the fixed end moments we have to represent somewhere here, okay. The fixed end moments for member AB, that is MF AB, it is minus 20.83. So, here I will not mention the units, units are kilonewton meter, because we need more space. So, it is 20.83 kilonewton meter, and MFBA, here I will represent it as plus 20.83, okay. And here that is MFCB. MFCB, as per our calculation, it is minus 4.69, okay. And MFCB, I will represent that here, that is 14.06. 14.06, and MFCD I will represent here as minus 25, minus 25, and MFDC here I will represent it as, it is plus 25, okay. So, this is the way of representation of fixed end moments in the Kani's table, right. Now, the next thing, in the step number 2, we have calculated the rotation factors, that is U. So, we have to represent the rotation factors. So, we have to represent the rotation factors here in the sides. In these boxes, we need to represent the rotation factor values. Now, for BA member, the rotation factor as per our calculation, it is minus 0.14 as per our calculation, and for BC member, I will represent here, it is minus 0.36, it is minus 0.36, and for CB member it is again minus 0.36, and for CD member it is minus 0.14. So this is how we need to represent the rotation factors. If you have 3 members or 4 members, then the corresponding rotation factors has to be represented either below or above, depending upon how the frame is. Okay. So once we do this, then next step is we need to calculate the rotation contributions. Okay. So see here, rotation contributions, that is m dash values. So here in the previous class also we have discussed, in the Kani's method we will try to calculate the rotation contributions only for the intermediate joints, not for the ends. It means we are calculating the rotation contributions only for the joints, intermediate joints, not for the ends here and here. So you see m dash AB, this is the rotation contribution at the end A, which we are not calculating or we are not worried. Similarly, m dash DC, that is the rotation contribution at the end, we are not calculating that value also. What we are working is, what we are calculating is these values, that is m dash BA, m dash BC, m dash CB and m dash CD. So we are working out or we are estimating only these rotation factors at the intermediate joints, right. Now as per our understanding in the previous classes, the rotation contribution m dash is equals to, okay, m dash is equals to, it is U, that is rotation factor, into algebraic sum of fixed end moments, algebraic sum of fixed end moments at any intermediate joints, plus algebraic sum of far end rotation contributions. So this is the formula, right. This is the general formula. Okay. So now we will start estimating these values 1, 2, 3, 4. In every cycle or in every iterations we need to calculate these 4 values. See here, in the first cycle, okay, in the first cycle m dash B, I will start with m dash B. I am not calculating m dash AB as well as m dash DC. So here if I want to calculate m dash AB, I need this value. Rotation factors we have already estimated. So I need fixed end moments at any joint. So algebraic sum of fixed end moments. See, at a point B we have 2 members, one is BA, another one is BC. How much is the algebraic sum of the fixed end moments? So that is plus 20.83 minus 4.69. If you add these two, that gives you the algebraic sum of the fixed end moments at joint B. So if I add these two, that is 20.83, I have to consider the sign also, minus 4.69 gives you 16.14, which I need to write inside the small box, right. Similarly here 14.06 minus 25. So 14.06 minus 25, it is minus 10.94. So that is the sum, algebraic sum of fixed end moments at joint C, which we need to represent in the small box. Now here to calculate the rotation factor, that is rotation contribution m dash AB. So I have to use this algebraic sum of fixed end moments, that is, before that, as I am calculating the rotation contribution for BA member, how much is the value of rotation factor, that is U for member BA. The rotation factor for member BA is minus 0.14. It is minus 0.14 into the algebraic sum of fixed end moments, that is 16.14 plus, this is very important here, algebraic sum of far end rotation contributions. So algebraic sum, as it is saying algebraic sum, we need to observe at joint B how many members we have and what are the rotation contributions of those members at the far end. See, at joint B we have two members, one is BA and another one is BC. So for BA member, which is the far end? Far end is A. So how much is the rotation contribution at far end A here? M dash AB? I don't know, because we have not worked out, so we will consider it as 0. And for BC member we have one more member, that is C as the far end. For far end the rotation contribution is M dash CB. At this stage in the first cycle we have not calculated this value, so I will treat this as 0. So here I will show a simple diagram, it will help you to understand. Whenever we are calculating the values at joint B, that is for BA and BC, to calculate the rotation contribution for these two members, we need to consider these values here. These values we need to use here. And similarly, when we are calculating the rotation contribution for this, that is M dash CB and M dash CD, we need to use these two values. Okay, we need to use these two values for the calculations. If you draw this, then it will be very helpful for you guys to understand it. Now see here, the far end rotation contributions. So far end rotations are, for B joint we have two members and these are the two far end rotation contributions. So right now these two are 0 because in the first cycle we have not done anything. So it will be 0 plus 0, 0 plus 0. This gives you a value of minus 2.26. Minus 2.26 kilonewton meter, which I need to write here below this, that is minus 2.26. So this is one rotation contribution value in the first cycle. Similarly, we need to work out M dash BC, M dash CB and M dash CD. All are exactly same. Now see here, M dash BC. Now to calculate M dash BC, again I will use the same formula, that is rotation factor. The rotation factor for BC, it is minus 0.36, minus 0.36 into the algebraic sum of fixed end moments. The algebraic sum of fixed end moments for B joint, it is 16.14, 16.14 plus the far end moments, the far end rotation contribution for B joint. These two are the far end rotation contributions. Right now they are 0. So I will use 0 plus 0. In the first cycle they will be 0, but not in the second cycle onwards. Okay. So this gives me a value of minus 5.81. Minus 5.81 kilonewton meter, which I need to represent here, minus 5.81. Right. Now M dash CB. So M dash CB, again I will use the same formula, that is rotation contribution. The rotation contribution for CB member is minus 0.36 into the algebraic sum of fixed end moment. So the algebraic sum of fixed end moment at joint C, it is minus 10.94 plus the far end rotation contributions. So what are the far end rotation contribution for joint C? They are M dash BC and M dash DC. So here M dash BC we have got value. So that I need to use in the calculation, that is minus 5.81. So here this value will be minus 5.81 plus the M dash DC, it is 0. It is 0. So this gives me a value of 6.03. 6.03 kilonewton meter. So that I need to represent here 6.03. Okay. Now the last value M dash CD. M dash CD. So again formula will remain same, that is U into algebraic sum of fixed end moments plus rotation contributions at the far end. So for CD member, the rotation contribution, so the rotation factor is minus 1.4. So it is minus 0.14 into the algebraic sum of fixed end moments at the joint C, it is minus 10.94. Okay. Then the far end rotation contributions for joint C, M dash BC and M dash DC are the far end rotation contributions. So M dash BC is minus 5.81, M dash DC is 0, that I will use here. It is minus 5.81 plus 0, that gives me a value of plus 2.35 kilonewton meter. So I will write that here 2.35. Okay. So this completes one cycle. This completes one cycle. So this is cycle 1 value. Now similarly we need to keep on repeating these calculations, all the 4 calculations, until we have the same iteration values in the next cycle also. See here, now if I go for the second cycle, cycle number 2, okay. In the cycle number 2, this portion will remain same, that is U and the fixed end moments, they will remain same. Only these things will be changing. Only the far end rotation contributions will be changing, or else the remaining will be same. Now for the second cycle, again if I start with the M dash BA, so M dash BA is equals to rotation contribution, so rotation factor into fixed end moments. This value will remain same, they will not changing. These two are same, they are not changing. So it is minus 0.14 into 16.14 plus the far end rotation contributions. For B joints, M dash AB and M dash CB are the far end rotation contributions. Now how much they are? Here it is 0 because we are not calculating the values, 0 plus the M dash CB. M dash CB here it is 6.03. Previously it was 0, but now it is 6.03. That gives you a value of minus 3.1. Minus 3.1 kilonewton meter. That I need to represent here. Minus, it is minus 3.1. Right. Now for the second value, that is M dash BC, again I need to calculate the rotation contribution. M dash BC is equals to As I said, rotation factor will remain same, the fixed end moments will also remain same. The far end condition, this value will remain same 0, okay, plus this value, that is 6.03. It is 6.03. You can see for the members of a same joint, only the rotation contributions, rotation factors are changing. The inside the bracket, the values will remain same. So if you remember this, you can just change the rotation factor value and you can calculate it, you will get the answers. That gives you minus 7.98, minus 7.98 kilonewton meter, which I am going to represent here, minus 7.98. You can see there is a variation in the values, they are not same. We have to do this cycle iteration values until we get the same values. For the next, that is for M dash CB, the rotation factor is minus 0.36 into the fixed end moment is minus 10.94 plus the far end rotation contributions, that is M dash BC and M dash DC. M dash DC is 0, whereas M dash BC in the previous cycle we have taken it as minus 5.89, but now it has to be minus 7.98. So this is minus 7.98 plus 0, that gives you a value of 6.81 kilonewton meter. So that I am going to represent here 6.81, right. Now for the last M dash CD, it is minus 7.98 plus 0 gives you a value of 2.65 kilonewton meter. So it is 2.65. This is cycle 2 or iteration 2. Now you can see we have done 2 cycles, 2 iterations, but the values are not same. So we have to go for the next cycle, one more cycle, that is cycle 3. So here also, as I said earlier also, there is only variation in these far end rotation contributions, all the others will remain same. Now for M dash AB, the far end rotation contributions 0 and this 6.81, 0 plus 6.81, that gives you minus 3.21, sorry, 3.21, and I will represent that here, minus 3.21. Okay. For BC, minus 0.36 into 16.14 plus 0 plus 6.81, that gives you minus 8.26 kilonewton meter. So that I will represent here minus 8.26. Okay. And for M dash CB, rotation factor, that is minus 0.36 into fixed end moments, minus 10.94, minus here the far end rotation contribution, that is these two values. So in this cycle it is this value, that is minus 8.26 and 0, minus 8.26 plus 0, that gives you a value of 6.91 kilonewton meter, 6.91, and For the m dash CD, it is 8.26 plus 0. That gives you a value of 2.69. 2.69 kilonewton meter. Let me represent this here. 2.69. 2.69. So this is cycle 3. You can see here, now even after the completion of the cycle 3, the values are not similar, but one thing what we can observe is the variation has got reduced. Here you can see 5.81 to 7.98, the difference was very high, but here 7.98 to 8.26, the variation has reduced. Might be in the next cycle we may get the exactly same values. So we don't know. So let us see. Let us go for one more iteration. So in the next iteration also, cycle number 4. In the cycle number 4, the rotation factor is minus 1.4 into 1.6. So this will be the 0 plus this value, that is m dash CB, it is 6.91. 6.91. That gives you a value of minus 3.22 kilonewton meter. Now you can see the variation has got reduced, minus 3.22, very close. This is also 0 plus 6.91, that gives you minus 8.3, minus 8.3 kilonewton meter. So it is minus 8.30. And for m dash CB, the far end moments are m dash BC and m dash DC. So here the new value for m dash BC is minus 8.3. So it is minus 8.30 plus 0. This is also minus 8.30 plus 0. That gives you a value of 6.93 kilonewton meter and 2.69 kilonewton meter. So let me represent those here. This is minus 8.30, 6.93 and 2.69. You can see here in the cycle 4, one value has got same, right? So obviously it means, and even the differences has got reduced. So if you go for one more cycle, you will get exactly the same values. That is, if you go for the cycle 5. So now if I go for the cycle 5, then it is 0 plus 6.93, which gives you exactly the minus 3.22 kilonewton meter. So 0.693, that gives you minus 8.30, and for the next cycle it is minus 8.30 plus 0 gives you plus 6.93 and this is also 8.30 plus 0 gives you the 2.69 kilonewton meter. So in the next cycle they will be exactly same. that is minus 3.22 minus 8.30 6.93 2.69. So whenever the values has repeated, so you can say that we can close the iterations or we can close the cycles, if because even if you go for the further cycles you will get the same values. So no need to doing the repeated calculations again and again. Correct? So what I will do, I will finalize these rotation contributions. So these are the final rotation contributions which we need to use for the calculation of the end moments. Now tell me one thing, what is the final rotation contribution for M dash AB? It is 0. It is 0, and similarly the final rotation contribution for M dash DC, that is also 0, right? So using this we need to go for the calculation of the final end moments, that is step number 4. Final end moments. So in the previous class we have seen an equation to calculate the final end moment, so that I will use and which will remain same for all the members. See, for example, if I want to calculate MAB, so as per our previous discussion it is MFAB plus 2 times of the rotation contribution at the same point, that is M dash AB plus 1 time of the far end rotation contribution, that is M dash BA. Now how much is the fixed end moment? So fixed end moment here it is minus 20.83 plus 2 times of the rotation contribution. So the rotation contribution at the same point is 0, so this whole thing will be goes 0. Next the rotation contribution for the far end, that is M dash BA. M dash BA here it is minus 3.22. Minus 3.22, that gives you a final or end moment as minus 24.05. Minus 24.05 as the final end moment at the end A. Now for BA, MBA is equals to, it is MFBA plus 2 times of M dash BA plus 1 times of M dash AB. For BA the far end is AB. So for this the fixed end moment is plus 20.83 plus 2 times of the M dash BA. M dash BA is 3.22 minus 3.22 plus M dash AB is 0. That gives you a value of 14.39 kilonewton meter. Now similarly for span BC, if I go for a span BC, MBC is equals to, it is MFBC plus 2 times of M dash BC plus 1 times of M dash CB. So MFBC is minus 4.69, it is minus 4.69 plus 2 times of the rotation contribution. How much is the rotation contribution at BC? The rotation contribution at BC is minus 8.3. Minus 8.3 plus M dash CB. M dash CB is 6.93. So it is 6.93. That gives you a value of minus 14.93 0.39. So you can see here at point B, BA and BC, they are equal and opposite. So if they are equal and opposite, then we can say that our calculations are correct. If they are not equal and opposite, then you can straightforward assume that your calculations has gone wrong. So please verify your calculations. In the similar way, if I calculate the remaining things, that is m dash CD, m AB, BA, BC, CB. M dash CB is equals to, it is MF CB plus 2 times of the m dash CB plus 1 times of m dash BC. So MF CB is 14.06 plus m dash CB is 6.93, so it is 2 times of the 6.93 minus m dash BC is 8.30, which fetches a value of plus 19.62 kilonewton meter, right? And for the last span, that is MCD is equals to, it is MFCD plus 2 times of m dash CD plus m dash DC. That gives me a value of MFCD is plus minus 25. It is minus 25 plus 2 times of the m dash CD. M dash CD is 2.69 plus m dash DC is 0. That gives me a value of minus 19.62 kilonewton meter. And lastly, for MDC is equals to MFDC plus 2 times of m dash DC plus 1 time of m dash CD. So it is plus 25 plus DC, m dash DC is 0 plus 2.69. That gives me a value of 27.69 kilonewton meter. So these are the final end moments as per the Kani's procedure. So once we calculate these end moments, we need to represent them into the loading diagram. Okay. So MAB, as per our calculation, it is minus 24.05. Minus 24 means it is a negative value. So we need to represent this as anti-clockwise in the direction. So here it is, so 24.05 kilonewton meter, and MBA, as per our calculation, we got it as positive value 14.39. So positive value indicates it is a clockwise in the direction. So let me represent a clockwise moment here. It is 14.39 kilonewton meter. So MBC, same value but opposite in the direction, anti-clockwise. So here it is clockwise. Next I will represent this. You can see here it is anti-clockwise, but the magnitude will remain same, equal and opposite. So the joint is in the equilibrium position. For CB member, you can see it is 19.62. It's a positive value. Positive value means it is clockwise in the direction, right? And MCD, we got same value but negative direction. It is anti-clockwise in the direction. So it is anti-clockwise in the direction. So magnitude is 19.62 kilonewton meter. For both it is same, 19.62. One is clockwise, another one is anti-clockwise. And lastly, for DC, it is plus 27.69. So it is a clockwise. it is clockwise, so it is 27.69 kilonewton meter. So this is how we need to represent the loadings in the main diagram. So in the problem we can observe that they have asked us to draw only the bending moment diagram, not the shear force diagram. So as they have asked only bending moment diagram, so we can draw the bending moment diagram without any further calculations. Okay. But if they have asked us to calculate the, so if they ask us to draw the shear force diagram also, then we need to go for one more step, that is support reactions and the maximum bending moment calculations. So that part is not here, it is not asked in this particular problem, but in the next problem they will ask, or it will be there in the given. So what I will do, I will straight away draw the bending moment diagram. So I will just extend the projection lines so that it is easy for us to draw the bending moment diagrams. Okay. So what I will do here, I will draw the bending moment diagram by superimposing the end moments with end moments calculated with the maximum bending moments. Okay, right. Now you can see the bending moment at A is, it is 24.09. So I will mention that somewhere here, it is 24.05 kilonewton meter, and here at B joint it is 14. So I will represent it here, it is 14.39 kilonewton meter, and here it is 19, so it is 19.62 kilonewton meter, and here it is 27. So here 27.69 kilonewton meter. So straight away you join all these bending moment values. Okay. Now for a span AB, if I treat this as a simply supported beam, okay, with a UDL, of magnitude 10 kilonewton per meter, okay, the maximum bending moment will occur at the center, and it is calculated using the formula WL square by 8. So here W is 10 kilonewton, better bending moment equals to WL square by 8. So W is 10, and the span is 5 meters, so it is 5 square divided by 8 gives you a value of 31.25 kilonewton meter, which I need to represent here. So as it is a UDL, so I am drawing the bending moment diagram as parabolic. So this maximum value it is 31.25 kilonewton meter, right? And for BC span, so for a BC span you can see if I treat it as a simply supported beam with the eccentric load of magnitude 25 kilonewton. So this is 3, this is 1. Here the maximum bending moment will occur under the point load, and it is estimated using WAB by L. WAB by L. So W is 25, A is 3, B is 1 divided by 4. that fetches you a maximum value of 18.75 kilonewton meter. So this is 14, 17, somewhere here it is very close. So this is 18.75 kilonewton meter. So this is 19.6, this is 14, means it will be just little above the line. Okay. And for the third span, it is a central concentrated load of 40 kilonewton is acting, and the maximum bending moment is calculated using the formula WL by 4. So the W is 40 kilonewton, L is total span is 5 meter divided by 4, that gives you a value of 50 kilonewton. So it is 50 kilonewton meter. So that I need to represent. So here it will go little up. Okay. Because of the concentrated load, the variation is linear. So this value is 50 kilonewton meter. So here what we do, we take this as the datum. We take this as the datum. Okay. So the bending moment diagram, above the line it will be positive, and below this we treat it as negative. So this also we treat it as negative. It is very little positive, this is negative, this is positive, this is negative. So here you can right. So this is how we need to draw the bending moment diagram if they ask to draw only bending moment diagram. If they ask to draw the bending moment diagram as well as the shear force diagram, then we will have to go for one more step of calculations, that is support reactions and the maximum bending moment. Then using those values we need to draw the shear force as well as the bending moment diagrams, right. So I hope you have understood how to use the Kani's method and how to calculate the rotation factors and the rotation contributions in the Kani's table, and how to use those rotation contributions to calculate the end moments. So what we have done here is, if I summarize, first we have estimated the fixed end moments, then we have calculated the rotation factors. So to calculate the rotation factors, we have gone with the same table of the distribution factor. So using the distribution factor values, we have gone for the one more step of calculation as rotation factors. So we have used those fixed end moments and the rotation factors to calculate the rotation contributions in the Kani's method. So we have done this calculation of rotation contributions repeatedly until we achieve the repeated values. So once we achieve the repeated value, we have stopped the cycles. So once we got these values, then using these values we have estimated the end moments. So this is how we need to use the Kani's method to analyze beam. Right? Thank you.